All right, so I'm going to go through this worksheet, but I'll also upload a PDF of the answer key so you can just refer to whichever one you need to, okay? Let me just get rid of some of this. All right, so the first problem has iron and cadmium. You can easily identify your anode and cathode based on what is happening to each metal, okay? So you have iron with a 0 going to +2, cadmium with a +2 going to solid cadmium with the oxidation state of 0. And when you start, you should remember your little helpful thing that helps you understand that, helps you remember. I just realized something. Helps you remember the anode and the cathode. So NOx red cat is the little device that you should use to remember that oxidation happens at the anode and reduction happens at the cathode. But another way to remember that is that the anode is the more negatively charged electrode because that's where electrons are going to come from. And anions are also negatively charged. So the root of the word, or like the prefix in the word, is basically the same. Cations are positive, anions are negative. Cathode is the positive electrode, and anode is the negative electrode, but also an ox red cat. Why not? Okay. So the oxidation happens at the anode, and the cathode is therefore cadmium. The cadmium 2 plus electrode is, what is that? Electrode is where reduction happens. So that's the cathode. Cadmium 2 plus is getting reduced to cadmium solid. So that is the explanation for why the cathode is Cd plus 2, okay? Or the cadmium electrode. Okay, then write the cell notation. So remember, cell notation is just separating oxidation and reduction. Iron solid vertical line is becoming +2 iron aqueous. Salt bridge is 2 vertical lines. Then cadmium +2 aqueous vertical line is becoming cadmium solid. Okay, there is your electrochemical notation for this galvanic cell. So remember the double vertical lines for the salt bridge. Okay, now let's calculate the cell potential. So we need the numbers from our actual standard reduction potentials table. Let me get this erased too. Right over here, I have iron 2 right there. The number for iron 2's oxidation. So iron is becoming oxidized, which means we must reverse the reaction. When you reverse the reaction, you must flip the sign. So that's positive 4,5. And then cadmium, where be cadmium? Oh, it's right above. It's a negative 0.4. So cadmium is going this way, iron is going in the reverse direction. So you can calculate your cell potential. Standard cell potential is equal to EOX plus E reduction. And that is going to be equal to 0.45 volts plus negative 0.4, negative 0.4 volts. And that is going to give you a total cell potential of 0.05 volts. That's your cell potential, okay? It's thermodynamically favorable. It's positive, so that's fine. Okay, next one is to sketch the voltaic cell, galvanic voltaic, same thing, okay? I got a picture so I don't have to draw beakers and whatnot, but remember to label everything with the correct charges and whatnot, show the movement of electrons and all that, okay? So I'm gonna say this is my iron. This is the place where iron is becoming oxidized. So iron solid is going to iron 2 plus 2 electrons. That is my oxidation, okay? And this is going to be my anode. And at the cathode, which is this side, I'm going to say cadmium 2 plus 2 electrons is going to cadmium solid. All right? So this is aqueous. This is aqueous. Oh, forgot the plus there. Okay. Now, we need a salt bridge. You can basically just say inside your salt bridge is some kind of ionic compound that is completely soluble, and that'll be like potassium nitrate or something. And on the side where iron is getting added to the solution, you are going to want to have potassium, sorry, not potassium, nitrate over here. NO3 minus ions should be going into the increasingly positive ion, and potassium ions should be going into the side where the cathode is, okay? It's kind of important to make that distinction. Okay, so we got our anode and our cathode. We got to also show the movement of electrons. So electrons are going this way. And if you were feeling fancy, you can say how many electrons. And also, if you were feeling even fancier, you can draw your voltmeter and draw the number in there. This is not necessary. I'm just being silly. Okay, so we can say that this end is negative, this end is positive. And before we forget, inside our solutions, we must have Fe2 plus. I'm going to say this is an aqueous solution of nitrate, iron nitrate, okay? And it's floating around. And then on this side, I'm going to say this is cadmium nitrate, because you need aqueous solutions to balance out. So I'm going to say these are both 1 molar concentration of CdNO32, and this is a 1 molar concentration of FeNO32. All right, I think we got everything. Got the anode, got the cathode, all the parts are labeled. We good. All right, so, oh, one last thing. I would like to write that this is solid iron and that this is a cadmium electrode right there, okay? All right, so let's do the second problem. Predict whether the following reactions will be spontaneous under standard conditions. Indicate your reasoning. If your E cell is positive, then you have a thermodynamically favorable reaction, okay? So in this one, copper, 0 goes to +2, copper is oxidized. So your oxidation reaction, oh, maybe I should stick to the same colors as the PowerPoint. I could if my eraser works. Okay, it does not. Okay, my oxidation reaction is copper going to copper +2 electrons. And then my reduction equation is 2 hydrogen ions plus 2 electrons going to H2. This will be a gas. This will be solid going to AQ. This is AQ. Okay, now you can see that the standard hydrogen electrode has a electrode potential of 0. So this is the reduction equation. So this is 0.00 volts. The E cell, not the E cell, the standard cell potential. This is why I don't do stuff on the board, kids, because my eraser just stops working and it is so annoying. Okay, so the standard reduction potential for hydrogen is 0, and copper is, where is copper? We need copper +2. There it is. Okay, there's copper, and that is nope, that's not it. This is copper 2 plus becoming, oh, right there. Copper 2 plus +2 electrons, that's 0.34. So this one is 0.34. Okay. Now in this particular case, copper is becoming oxidized and is going in this direction. So we got to flip the sign of the 0.34, which is positive, to negative. Okay. So this is E ox and this is E reduction. So if you calculate E cell for this one, that's equal to the oxidation, which is negative 0.34 volts plus 0. This E cell is going to be negative 0.34 volts, and therefore this is not thermodynamically favorable. Okay, so this reaction having a negative E cell, I did the same thing. Okay, is not thermodynamically favorable. Not TF, because E cell is negative. Okay, you can kind of predict what delta G should be, right? Delta G should be negative, E cell should be positive. Look at us connecting things. Okay, so lead is going from 0 to +2. Silver is going from +1 to 0. So oxidation is lead, Pb going to Pb +2 electrons. Reduction is 2 silvers going to, do we need that? Okay. 2 silvers plus 2 electrons. 2 silvers plus 2 electrons going to 2 Ag. Solid AQ, solid AQ. All right. So this is definitely something that happens because, I mean, you probably have some knowledge of the activity series. Lead is definitely above silver, right? So here is lead. And where is my silver? Can't be low, must be up. There is silver. Okay, so silver's potential is 0.80 volts, okay? And lead's potential is negative 0.13. So lead is being oxidized, right? So reverse the direction, flip the sign here to positive. Got to switch it to positive. So E cell is equal to 0.13 volts plus 0.80 volts, and that is going to be 0.93 volts, which is a positive number. This is thermodynamically favorable. Check.